used uh, we these are the different machines which are being used currently in order to make the different membranes to get things done. Like there are basically two types of two shapes of membranes. One is a flat sheet membrane, another is a hollow fiber membrane. The hollow fiber, we have just seen the cut section, how it is the cross section, how it is separating and things like that. In order to make a flat sheet membrane in a lab scale, we can use a doctor's plate as seen here. And in the industrial scale, we are actually going for the roll to roll machine. This is a roll to roll machine, meaning that we are using multiple rollers so the continuous sheet can be formed. Here in doctor's plate, we can actually make only individual layers like A4 sheet, 300 millimeter size sheet, 500 millimeter size sheet, all depending on the size of that particular flat sheet casting machine. And how the casting is done, it's a very fundamental thing. Like first we have to make the polymer dope solution by dissolving whatever polymer materials that we are using, and we are casting on the surface. And then the phase inversion methods, we will discuss that in detail, how the phase inversions affecting in the upcoming slides. So these are the machines. This is the another type, the hollow fiber. Here we can see the hollow fiber being spun in the industrial scale, the original image of a hollow fiber manufacturing unit here. This is the diagram, the schematic of that particular machine, where we are having a this coagulant bath, the wash bath, everything, the spin rate, everything that we'll be discussing later. So as I was mentioning about the different materials that are currently used to make the polymer dope or the polymer solution, some very commonly used materials are there. Number one is polysulfone. Polysulfone is having a wide range of application, whether it can be in water purification or gas separation, and specifically in industrial wastewater treatment also. These are very commonly used because it can be dissolved very easily using certain solvents like NMP, PMAC, DMSO. That also we will discuss in the coming uh, slides. So that is number one, polymer. Another one is polyether sulfone. It is actually a better form of polysulfone. Recently, we have shifted more from polysulfone to polyether sulfone whenever the application involves higher temperatures, because the temperature withstandability of polyether sulfone is much better when compared to polysulfone. So it is also used in whatever application polysulfone can be used. And the major difference is the hot water system, where the, as I mentioned, the temperature is coming into play. Another is polyvinylidene fluoride, which we call as PVDF in short. It is one of the strongest polymers in the sense, the hollow fiber which is spun using PVDF, or the flat sheet which is made using PVDF, is having a much better mechanical strength, and it can withstand all the higher pH conditions, as well as it can be used for multiple applications, not just in water purification and gas separation. Can be used in fuel cell membranes and other application where the layers are used in between. This is a very upcoming recent polymer, which is polyether imide. The trade name is Ultem, which is made by one company called as Sabic. So here, these are all these are all the improvements that the chemistry people around the world are working on in order to improve the how the durability, as I was telling, the strength, the durability, and the pH resistance, and all these things. And along with that, lot many gas separation principles are being tried out with such kind of materials. You know, the gas separation principles also we'll be discussing in the coming slides. The strongest among the recent ones is polyamide Torlo, a very greenish in color and extremely stronger, having much better tensile strength more than Altum. So on a scale of mechanical strength, this Torlon will come on top, even better than Altum and PVDF. So this is also much more into O2N2 separation and hydrogen separation, and specifically into gas separation, utilizing different gas separation principles. So these are the recent modifications of utilizing multiple materials and to make a mixed matrix membrane, and the utilization of metallic organic framework, which means a combination of polymers and different other materials like zeolite and other metal organic frameworks in order to make certain particular application work. All these are basically into higher order separation of water purification as well as gas separation, and encompassing all the applications which can be done using polymeric membranes. Even though gas separation and water purification are the major things, it is polymeric membranes are used in other applications like food packaging, where the moisture and the passage of microbes into the intruding into the food materials, the prevention can be done. Lot many works are being conducted, especially using different materials which are sustainable, like nanocellulose, and mineral and mining, and food and beverage, as I mentioned, packaging, and petrochemicals, air filtration, like that. So we are now gradually shifting into the gas separation using polymers, which actually is a very hard thing to do, because we all know that water purification is much easier when compared to gas separation because of the size and the easiness in handling, because handling gas is a very hard thing to do. And these are the different principles which are making the gas separation possible. One is solution diffusion, another is molecular sieving, another is facilitated transport. Solution diffusion, here, as we can see in the image from the left side, say a mix of gas is coming from the left, and say this is the polymer which we are using, one particular polymer, another one. So this particular polymer is making use of solution diffusion, another particular polymer making use of molecular sieving, another is making use of facilitated transport. And our target, here we can see the target separation molecule is the red one. Say this is CO2 and this is CH4. So the target molecule is the CO2 here, the black and the two reds representing CO2. The gray force and the red black in between represents methane CH4. So solution diffusion principle is that the CO2 will gradually dissolve into, it will be absorbed on the surface, it will be absorbed into the polymer, and it dissolves and it diffuses and it desorbs to the other surface. And this kind of gas separation principle is called as solution diffusion. And in the next one, molecular sieving. Molecular sieving, as the term suggests, it is a sieving mechanism. CO2 being a smaller gas, smaller gas in the sense it is having a smaller kinetic diameter. Kinetic diameter is the space that each particular molecules are taking while passing. So it will be excluded. This methane will be excluded and only CO2 will be passed through. And the third one is the facilitated transport, which was my area of work during my PhD. Facilitated transport means we are making use of certain particular materials which are having higher affinity to different gas molecules. For example, CO2 being a highly reactive gas. A reactive gas in the sense we all know that we all are using soda in some forms to drink for drinking, and for other applications we are using soda or cola. CO2 reacts with water to form the carbonic acid. So with the presence of moisture and with the presence of other CO2 affinity material, the CO2 can be quickly absorbed and passed through, which the transport of CO2 is facilitated making use of the water molecules as well as the different uh, CO2 affinity molecules or the materials that we are using. So, as I was mentioning, this is more into the different kinetic diameters. You know, the gas molecules won't pass like a bullet. It won't pass in the straight line. It will always be moving here and there, and it will be slightly swaying during its motion. And these are the kinetic diameters, and this comes into play when the molecular sieving effect is taken care of. Hydrogen being the smallest of the molecule, and here methane is the largest, so like that. So this is another type of gas separation mechanism where making use of fractional free volume of the polymer chain is taken care of. The fractional free volume, in a nutshell, I'll tell you that it is the amount of free volume which is left after the polymer chains are stacked inside. There will be some gap left which is in the angstrom level, as seen in the previous slide. If the free volume is in the range of 3 angstrom or 3.2 angstrom here, then the gases which are having higher kinetic diameter won't pass through, and the lower kinetic diameter will pass through. So that is the principle here, making use of free volume. So this we have already mentioned how the solution diffusion and the facilitated transport is happening. Here also the driving force is the concentration, the pressure difference, and the temperature difference across the feed side and the permeate side. And facilitated transport, I think I have given enough explanation to that. The CO2 affinity materials will help in the selective and the fast transport of CO2. And these are the materials which can be used if sustainability is a main thing, because the nanocellulose being a natural fiber, so it is a good thing that if we can make use of nanocellulose. And it is the another good thing about nanocellulose is that the reactive surface is full of hydroxyl groups, and hydroxyl groups means it is more affinity. It is having more affinity towards water, and that will help in absorbing more water, which will directly help in the CO2 transport. So these are the materials, CNC, CNF. These are the materials which are used, and the other materials which are used along with the CNC for the better compatibility and making this work are polyvinyl alcohol, sodium hydroxide, L-arginine. All these are having a common thing called as hydrophilicity, as well as the CO2 affinity. So This was my work during my PhD. As I mentioned, it was targeting on CO2 separation from methane, which means it is the combination, with the major combination in biogas as well as natural gas. It combinedly forms around 99 percentage of the total combustion of biogas. So biogas being a freely formed fuel, having a high concentration of CO2 of 30 to 40 percentage, it can be reduced, and the methane can be enriched, it can be utilized. So this was one particular design that we tried out. So we worked on this, and making use of the doctor's plate. In the starting, I discussed about making the thin films on a lab scale as well as a industrial scale. And the lab industrial scale, we are going for the roll to roll for the continuous uh, formation of the sheets. But in case of lab scale, we only need to make one sheet, and these were the different combinations of uh, uh, the dopes that I used. And here the method of preparation, the film casting, the drying, and the peeling of the films, and the cut sections of these films are all given, and this was taken to find the mechanical strength. How much is it increasing with the increase in concentration of nanocellulose, like that. So this was a very, frankly, a very crude way of doing things at that point of time, because uh, we only wanted to do it in a very small scale. So uh, we actually purchased the hollow fibers. We did not spin the hollow fibers. We made the composite, and we dip coated, dried, and then conducted the experiments. So this was the dip coating, the dry. Is the permeability and the selectivity equation that was generally followed. The major parameters which are affecting the permeance as well as selectivity. Uh, the, the permeance is the amount of gas which can pass through, and selectivity is the selective transport of the gas. For example, through a membrane, if the transport is happening, the passage is happening at a higher rate, but if the purity of the separated gas is very less, we can say that the selectivity is very low and the permeability is very high. So there is always a problem. If we really want to increase the speed, we can, in general, we can say that the speed of the separation is very high, which means the permeability is very high. Then the selectivity will be very much affected. Selectivity may go down. And if we really want to improve the selectivity, the separation quality need to be improved, the purity needs to be improved, then the chances of the permeability getting affected is there. So this is another setup which we used in order to get a higher permeability as well as higher selectivity. Instead of using the previous one, was more like a staggered arrangement, which were having its own problems in replicability. This is a more common or commonly used hollow fiber module design, where the modules are stacked, and it was uh, fixed on both the sides using epoxy, and then passed through and getting separated, like that. So this was uh, the selectivity and the permeability that I was talking about. Here, one uh, graph is there, which is called as the Robson upper bound, and the target is to cross the Robson upper bound. Here, the x-axis is defined by the permeability, and the y-axis is defined by the selectivity. And going to the right side, the permeability will increase, and going towards the top, the selectivity will increase. So everyone's target is to go to the top right end, right? Uh, but which is not really possible. So this graph actually compiled all the data of all the different gas separation experiments which were conducted using the different polymers, and some plots, some bounds were drawn, and people are trying to cross this bound and saying that our permeability and selectivity both are very high. And in order to make this happen, many other works are being conducted, many specialized works are being conducted. And the major thing is the functionalization of the polymers that we are using. Here, as I mentioned, nanocellulose being used as a sustainable yet CO2 affinity material. The hydrophilicity of nanocellulose was improved by different functionalization method in order to improve the permeability without any reduction in the selectivity. One such application is phosphorylation, where we are actually imparting phosphoryl group PO3 minus randomly, replacing the OH groups in order to improve the hydrophilicity and thereby improving the permeability without affecting the selectivity. So this was the steps involved, the method that I adopted to make the phosphorylated nanocellulose powder to do the separation. Another one is carboxymethylation. Similar to phosphorylation, here we are replacing the OH groups with the carboxymethyl groups, and which is actually similar to the phosphoryl groups in imparting high hydrophilicity and higher CO2 affinity in order to improve the CO2 permeability happen without reduction in the selectivity. These were the steps which are involved in order to how to make the carboxymethylated nanocrystals. Now, coming into the different preparation of a thin film as well as hollow fiber strategies. Moving from the lab to the industry, I actually conducted the complete set of works involving the starting of the weighing of the polymer to the spinning of the hollow fiber and the coating, and the complete spectrum is included currently. And to in order to make a flat sheet or a hollow fiber membrane, these are the steps involved: the proper selection and the weighing of the polymer or polymers, different set of polymers that are used, and the most commonly used and effective solvents. These four are the most commonly used solvents, which are having certain problems with it, with the environment. That is another set of challenge. But these are the highly effective solvents which are used, and the fundamental dissolution method which everyone is using is the hot plate magnetic stirrer. For a lab scale and pilot scale manufacturing, we can use the hot plate magnetic stirrer, and in big industries we'll be using the huge metallic cylinders. Inside that, the mechanical stirrers are being used with the motors and all. And here, after the dissolution, the identification has to be properly done using different method. The most fundamental thing is to see through whether any clumps are there, or it is not more, the dissolution is not complete because of the presence of highly viscous or thick solutions in between. And after the identification, and then we can go for the hollow fiber spinning or the flat sheet casting. So this is the flat sheet casting, the simple method. as I was telling in the starting stage itself, in order to make a flat sheet after making the dope solution, the polymer solution, and after pouring on the doctor's blade glass substrate, then different methods can be adopted. One is keeping it in the open to dry by itself, or we can use another method called as non-solvent induced phase separation. Non-solvent induced phase separation means that we are using a non-solvent. Water is a non-solvent, and if you are going to directly immerse this the cast polymer film into water, this non-solvent water will enter into the cast polymer film, and a separate layer will be formed. That is called as non-solvent induced phase separation, where we are simply dipping the glass which is casted using the polymer uh, in order to make the membrane. This is the hollow fiber spinning machine schematic, where we are using a spinneret in order to spin the fiber, where from a tank the polymer solution dope is taken, and this spinneret is nothing but an extruding part, where it is extruded and it will be directly entered into a non-solvent bath, just similar to the non-solvent bath where we are using here, in where we are dipping the glass substrate. Here we are actually passing the formed hollow fiber, the semi-formed hollow fiber into the water in order to make it proper, and it will be passed through the set of rollers to make it strong, and the washing of the solvent, the NMP and the other solvents which are being used, and then keep it in the bath for some time for the proper washing, and then the drying, and like that. So, as I was mentioning about how the non-solvent induced phase separation is really affecting or making the membrane, after making the clear dope solution, we know that it actually dissolved into the solvent. So it is in a very happy phase, like, it is with a solvent, it is dissolved into a solvent. Suddenly, if you are going to put that into water, what will happen is that water is a non-solvent, it cannot dissolve anything, but it is having a high affinity to remove the already present solvent over there. The phase separation of the polymer will happen. The solvent which we are using, the NMP or DMAC or whatever, it will go out and the water will enter through. And because of that, based on the speed at which we are using and many other parameters are there, I'm not really going into that. We can make different internal structures, and then we can make the different polymers, the polymeric membranes, for our own purpose, whether it can be highly porous or highly dense or continuous or not so continuous, all for different set of applications. So, as I was mentioning more about the non-solvent induced phase separation, this is the representational image which was discussed earlier, where we are actually simply putting the dissolved and cast polymer into the water, the non-solvent water, and we are getting it separated. Similar to that, instead of using water, if we are going to directly pour and naturally cool down from a higher temperature, if you are using a very high temperature dough and we are not using water instead, because of the normal cooling happening with the atmospheric air, then it is called as TIPS, the thermally induced phase separation. And the third one is WIPS, where vapor induced. This is nothing but we are casting a polymer dope solution onto a surface, and we are keeping it in an area where any vapor is there, for example IPA, ethanol, or any kind of ethanol is kept open, and that vapors will slowly interfere into the dope and making different kind of structures. So these are the three parameters which we are actually affecting the membrane formation. One is the evaporation time, how much time that we are keeping, how much time that we are, if we are going for the normal drying process by keeping it in the open, how the evaporation time is affecting. Or if we are going to use a vacuum oven, how much time, at what temperature, at what negative pressure that we are keeping, that all come into play. And there is a coagulation bath temperature. As I mentioned, the nips will happen only if the polymer solution is dipped into the water, where water is the non-solvent. And if the nature of the membrane formation is highly affected by the temperature. If the temperature is high, the coagulation bath temperature is high, the skin of the polymer will be extremely porous and weak. If it is very cold, for example 4 degree or 5 degree, then it will be extremely denser and can be used for gas separation applications, some other niche applications. And another important parameter is the viscosity of the dope, like what concentration of the polymer that we are using. For example, a 15% PVDF polymer in solvent will be having a lower viscosity when compared to a 20% concentration. So like that, the higher viscosity will yield a thicker walled hollow fiber, as well as a thicker flat sheet, which is having much better strength. But there is a range where we should be going for. The viscosity should not be too less, and it should not be too high. And these are the different characterization methods, as you can see. The fundamental things that all the membrane people are using. One is the viscosity meter. We are using a NDJ, it is viscosity meter, and we can find the rheological study also, because almost all these polymers, like PSF or Altum, all these are shear thinning, which means that with the increase in the rotam, the knob speed, it behaves like a thinner liquid. And if the rotation is very at the lower RPM, it will become more thicker. So such kind of studies can be done in order to see how the polymer is forming. Another one is the cloud point titration. As I have mentioned, cloud, it is a simple titration that is very commonly practiced just by taking a sample of the dissolved solvent. And if we are adding drops of water, we'll get to see at what point the color is changing, it is affecting like that. Light scattering is nothing but making use of light, like UV light or any other particular kind of light, to see the formed the dissolved solution is proper everywhere, it is uniform. And another is the capillary flow porometry. And capillary flow porometry, it will define the average pore size of the hollow fiber. We can find out by passing through a low surface tension liquid like gold wick. Normally a liquid called as gold wick is used, which is having a very low surface tension of even lesser than 20 kilonewton per meter. And the other ones a bit less used because of the high cost involved, the scanning electron microscopy and the atomic force microscopy. These images are of the scanning electron microscopy, where we can see through how the formation happened of the pores, the size of the pores, and the nature of the pores, like that. Atomic force microscopy will give you an understanding of the surface roughness of the formed film or the fiber. So these all we have more focused on making in a lab scale, and from lab scale to production scale, uh, there are few bottlenecks. One important bottleneck that everyone's facing who are working on CO2 separation is the plasticization. Here you can see the, I mentioned about the fractional free volume earlier as the smaller gap in between the packed polymer chains. And if we are using certain polymers like PSF or Altum or whatever it may be, if we are using for CO2 O2 separation, CO2 N2 separation or CO2 CH4 separation, the CO2 molecules will gradually get adsorbed onto the surface of each polymer chains, and gradually it swells up, and the free volume will be increased, so that the polymer chains mobility will be increased. And because of that, what will happen is that the permeability will increase at the loss of selectivity, which means that the gas separation won't really happen, but it will allow all the gas to pass through. So that is one bottleneck that generally we are facing. So in order to prevent the plasticization, the most common technique that we are using is cross-linking, and the another thing is the use of a copolymer. A copolymer means, I mentioned about Torlone earlier, polyamide. It is a copolymer. It is having a combination of different amide as well as imide. One other example is Pibax. Pibax is polyether block amide. There is an ether group as well as a amide group. So it is like, here we can see more of strengthening it. In a general term, we can say as giving pendant to the necklace. You know, if you are having different pendants in the necklace, we are actually imparting the strength like that. So that is the most common thing that we are using in order to improve the nature of the base polymer to make this happen. And other methods are also there which are still not industry viable, yet somewhere we are using making use of the 2D nanomaterials like carbon nanotubes and glass fibers like that, and the other methods like the making the temperature management and the lower operating pressures like that, in order to reduce the effect of this like that. Another one is another one major bottleneck is physical aging. uh, uh, Excuse me, 1 second, I'll be back, 1 second. Really sorry for that. Okay, so another thing is physical aging. Physical aging is actually the opposite of plasticization. Plasticization is actually expanding the polymer chains. Here, physical aging is because of the continuous usage, and over a long period of time, what will happen is that it the polymer chains will form a denser network which reduces the gas flux. So this is the opposite effect of plasticization, physical aging. So here also the preventive methods that we are doing are the same. We are their use of in order to withstand uh, the plasticization effect. We are giving the block polymers and doing making use of CNT and other thing. Here also we are actually doing the cross linking in order to maintain a stable and a strong bridge of polymers, where the the issue of getting compressed together and reduced gas flux can be reduced by using the making use of different scaffolding locks and the making use of mixed matrix membranes. So the lab scale, pilot scale, and the industrial scale. The apart from this plasticization and physical aging, the other challenges in industry that the membrane makers will face. The most important thing is the fouling and scaling associated with that. We all know how the RO membranes are working. Almost all of us are having the water purifiers, and inside the water purifiers, we are making use of a RO membrane. Every 6 months or 1 year, we are replacing that. That is because of the fouling that is happening. So that is one challenge. Another one is the improvement of the mechanical strength to withstand, and also to how to reduce the production cost, as well as the repeatability of the performance under real conditions. For example, certain times with the same composition, with the same membrane preparation methods, we'll be getting almost similar kind of membranes. We may be having much better results also, but repeatability won't be there. So that is one real challenge out there. So this challenge actually happens more when we are going from the lab scale to the manufacturing scale. The problem involved is that in lab scale we are using batch controlled small solutions, but in industrial scale the continuous manufacturing is happening, where the fluid shear variations are there. As I previously mentioned about the effect of shear thinning in most of these polymers which we are using at a higher mechanical stirring rates compared to the magnetic stirrers, the total nature of the polymer dope will be completely different, and the evaporation gradient and the tension forces associated with that will come into play, and that will result in the production of hollow fibers and flat sheets, which are of the same composition but of different quality when put into practice. So this pilot scale is actually a bridge between the lab scale as well as the industrial scale, where we are not really using the 50 ml lab jar and that jerking of using from 50 ml lab jar to a 500-liter vessel can be reduced using the pilot scale. In terms of pilot scale, it is like a medium scale production, an improved version of a bigger version of lab scale inside the lab itself, and the sizes of the products formed are also bigger when compared to the lab scale one, but not that higher when compared to the industrial scale. In the another one challenge there in industry is that the systems will be operating continuously. Here we can see the bigger the stirrers where the liters of 500 liters or 200 liters or that much capacity dopes are taken care at the same time, and it is continuously working place, and then the cleaning protocols and the module bypass options and all the things associated with that, because of the use of different machinery when compared to the lab scale, is the real challenge. So based on all challenges, in reality membranes are actually made into 4 different configurations. Here two configurations are actually made. One is tubular and the another is the plate and frame. These two are a bit of, this tubular kind of thing is effective, but it is extremely costly, where we are literally making use of a lot of metals and because of that, the fouling also will come into play. So we need to replace that also, as well as the cost involved is very high. The another one is a simple stacking of different flat sheets and making a frame to hold it. It resembles an electrolyzer stack, but the main disadvantage is that it is having a very low packing density, which means the total area to be used is very less, which actually makes it less effective. The other two are very commonly used nowadays. One is the spiral wound, another is the hollow fiber module. These are the most widely used ones. This spiral one we all know, as I was mentioning about the reverse osmosis module, the RO module that we are using. It is making use of a spiral wound machine where flat sheets are taken and flat sheets are rolled into one particular cylindrical shape and it is being used. As we can see, the membrane is kept in between and some spacers, some porous spacers are kept on top of that and rolled onto that, and then we'll be using epoxy to fix it, and the feed water is passed through and the permeate and concentrate will come through as seen in the figure. The other most important thing is the hollow fiber membrane module. Here at the bottom, we can see the hollow fibers are stacked inside a module where both the sides are fixed using epoxy, and the feed can be passed through the shell side. We call this the shell side. From the sides, we call it as the shell side, and from the ends, we call it as the lumen side. We can make use of any kind of separation. So, as I was discussing about the different the shapes or the different modules which are being used, considering all these aspects, in academia only the pure and the single gas are used, where the industry requires the membranes to handle the complex, the dirty, which is a very hard thing, and variable multi-component feeds. And another major thing is that during academics, people are only focused on, including me during my academics, we are all focused on showcasing that our work has successfully crossed the Robson upper bound, which means that the permeability as well as selectivity both increased at the same time. But in industry, it is completely different. Industry, they will think about how to handle the dirtiness, which goes into the scaling as well as fouling as well as operating at continuous levels. All these things will come into play. So, in order to make this work with the minimum polymers without making use of all the different materials like the nanomaterials and the other costly materials which are involved, certain engineering approach can be used for the base polymer. Certain industries will go for the synthesis of the polymer itself, where the molecular weight of the polymer will be adjusted as per their use. For example, polysulfone and polysulfone is particularly very good in that 50 to 100 kilodalton range. For your information, this dalton represents to the molecular weight of the polymer, which means 1 gram per mole represents 1 dalton. So 1 kilodalton means 50 kilodalton means 50,000 gram per mole. That is the molecular weight of the polymer which is used. So a low molecular weight means that it is very weak and the susceptibility of plasticization is more, and very high molecular weight means that it is highly viscous and it is very hard to process. So like that, there is a trade-off between these two. And people are using cross-linking strategies, as I mentioned previously, adding certain just like a necklace. If you are giving a pendant to a necklace, that is one cross-linking strategy by making a copolymer. or making the modifications like chemical modification directly onto the polymer in order to improve its different parameters like strength or porosity or whatever strength or molecular weight or whatever we want to improve, and also the monomer selection in order to make the polymerization, and all these post processing treatments like annealing, which is very important if we are going for hollow fiber. After making that, in order to make it proper, the surface strong with the proper tension, annealing and associated works are very much important, and surface modification is required, especially if we are going for an O2 N2 separation. There is no significant change in the size of O2 and N2. O2 being 3.46 and N2 being 3.64 angstrom. It is a matter of 0.18 angstrom. So it is very hard to differentiate both and do it. So the surface modification to make such niche applications work like that. And this is about the packing density, which I was mentioning a bit earlier. You know how the flat sheet and how the hollow fibers are getting used. You see the plate and frame kind of thing. In order to stack all the flat sheet will take more space, and the packing density is also very low. Whereas a hollow fiber will be very compact, and the surface area as well as packing density both will be very high. So membrane modules, the cost involvement is another thing. We have to actually make an average $10 to $50 is the cost implication per meter square. Anything more than that, that will make the operational expenditure very high, the OPEX very high, and the replacement cost also will add to it. This fouling and scaling mitigation, I mentioned about the fouling issues while making use of the polymers. Influence and all these things which are coming through it. So these are the different methods in industry where we are more focusing while making it also. The surface hydrophilicity, if the hydrophilicity is more, then the fouling can be reduced. So purposefully we will be tuning the chemistry in order to make more hydrophilic group to reduce the fouling, and also the charge modification by making use of the sulfonated or carboxylated PSC or PES. Very much related to the work that I did for my CO2 CH4 separation, and the cross-linking in order to reduce the swelling, because of the continuous use of a membrane will help in the swelling. So the scaling is an issue. The reduction of hydrophilicity is an issue. The cross-linking is an issue, and certain applications require amphiphilic segments where the Switzerland polymers, PEG, etc., can be used in order to reduce the scaling as well as improve the compatibility and self-cleaning applications. So, based on all these things, the projects which are coming, the academic projects which are coming, can make note of all the things from crossing the ropes on upper bound or getting a high selectivity, or to evaluate the membranes not just in the lab scale, not just to see what is happening in the lab scale, but to go out to the industry and try it out there in the realistic condition to see how it is happening. In that way, an approach to doing the work can be more beneficial to to the people who are conducting the work, as well as to the industry, as well as there will be a connect between the academy and the industry. And these things which we focused on, how to make the long term work with the less scalability, with the scaling and fouling and all these things. And in order to make that the polymeric fibers or the thin films based on that. And yeah, and to do the economic analysis to see how much amount of money is actually getting used in order to make that, in order to work for a longer period of time. So these are the major things are coming into play. And this actually, I'm not really into the AI for polymer design, but recently, I'm not going to discuss this part. This AI has been the whole team of our FDP is also rooted in AI. I know that, that's why I purposefully kept this slide here, so that many people are working on the prediction of the dope thermodynamics using the machine language model, and also the polymer structure and the property relationships are all being very successfully done recently. And this high throughput screening is a AI method which is seen recently in the last 2 years, is seeing developing. I just wanted to add one thing to this from my point of view. Uh, Making use of AI in the sense, uh, the understanding and the fundamental understanding of the polymers, and the prediction can be done by AI if we are going to give the different combinations, and if we are going to give the target which we really want to, then AI can actually help us to formulate certain compositions which may work. Frankly, that is the way that I am working for many of my works. So I just wanted to share that to you. So based on all these things, we can see how um, the gap between the academia and the lab where we are working in terms of making membranes, not just to do certain coatings and do one separation experiment in the lab. If we are able to make a module which can be worked in real time conditions, which we are actually making the membrane, taking care of the chemistry part which help in the long term run, and making use of, if possible, the AI tools can actually really help in bridge the connectivity between the academia and the industry. Thank you.
Thank you, Nithin. So, audience, if you have any doubt, you can unmute yourself and discuss here.
Please feel free to ask anything related to what I have discussed. If you are not really engaging, it won't be a great thing, right? No one there?
I think there are no doubts, Nithin.
Sorry, Mother.
Yeah, so I think the participants do not have any doubt. The session was very interesting. So,
Okay, I will think I can share my PPT for all the participants if they are having
sure.
any doubts, and if they really want to, we really need some help regarding doing work or something like that. They can freely approach to me. I can share the
Yeah, yeah.
PPT.
Sure. I'll share your number also. If they need, I'll share your number and email ID. They can
Yeah.
contact you. Sure. Thank you, Nithin. So, on behalf of Sripati Institute of Management and Technology, I would like to thank you for this wonderful session. I really enjoyed this presentation. Most of the slides were the session was very informative. I like the way of presentation, and once again, thank you for this wonderful session. Thank you.
Thank you, Mother. Thank you all
So,
participants. Thank you.
so with that, we will conclude our day 2. Day 3, we will start our session tomorrow. Tomorrow, first session will begin at 10. So I'll share the feedback from here. We can meet tomorrow. Thank you. Please, everybody, please fill this Google feedback form. Thank you, Nithin.
Thank you. Bye.